For Amir, he's going to be talking about flow characteristics.
Hi everybody, I'm Amir, PhD student at Clarkson University, and Abul, my advisor. My talk is a little different from yours, probably, because I'm not a fish biologist. I talk about mean and turbulent flow characteristics within an area of boulders with different boulder spacing. Let's talk about boulders. Boulders, or as we call them, roughness elements, are main elements in many restoration designs, like dam removal, retrofitting culverts, and also nature-like fish passes. The flow around boulders can be really affected. The boulders can change the local flow field, and this change can affect the aquatic life surrounding the boulder. So we are interested in knowing the relationship between aquatic life and roughness elements like boulders. A common approach to study the suitability of fish passage is studying through mean velocity, mean depths, and also substrate size and type. But recent studies have shown that there is another important parameter too, that is turbulence. Turbulence parameters can be very important too, can affect the fish behavior significantly. Turbulent parameters like turbulence intensity, turbulent kinetic energy, Reynolds shear stress, vorticity, and eddy size. In the right side of this slide, you can see effects of turbulence on aquatic life. It can affect the feeding behavior, habitat selection, swimming performance. And on the left side, you can see some studies that studied the effect of turbulence on some specific fish species, like juvenile Atlantic salmon, creek chub, Iberian barbel, juvenile rainbow trout, and western black-nosed dace, and many other studies. It is just samples, so it's important to know the role of turbulence in a fish passage. So let's talk about some basics of flow field around the roughness element like a boulder. Behind the roughness element like boulder, there is a wake region. In this region, the velocity decreases significantly. So it can act as a refuge zone for fish and other species. Also, we can classify roughness of a bed based on to three flow regimes. Based on the distance between roughness elements. These three types are isolated roughness, wake interference, and skimming. In the isolated roughness, the first one, the roughness elements are far from each other. So the vortex generation and recirculation zone downstream of the roughness element is completed before reaching the next element. In the wake interference, it's not completed. Actually, it interferes with the next element. And in the skimming, the roughness elements are so close to each other. So we just have some stable vortices in between. The objective of our study was experimental investigation of mean and turbulent flow characteristics within a single straight area of boulders with different boulder spacing under different flow rates. A quick review of our experimental setup. We did our experiment in hydraulic lab of Clarkson University. The length of our flume was 13 meters, the width was 0.96 meters, and the slope was 0.5%. We selected a specific zone in our flume as the tape measurement zone. The length of this part was 2.4, and it was 3.8 meters downstream of the entrance of the flume to make sure that the flow is fully developed in this area. Also, we used a gravel bed with D19 about 28 millimeters, D15 of about 17 millimeters, and D10 of about 9 millimeters. And as roughness elements, we used natural spherical shaped boulders with a mean diameter of 12.5 centimeters. To measure the flow field, we use a vector-like DV. It can measure three-dimensional velocity field. And the sampling rate for it was 25 hertz with a sampling volume of 5 millimeter. And the measuring point was at a relative depth of 0.25. It was actually an outer layer of the flow, not very close to the bed. So we designed 4 scenarios for our experiments. The scenario 1, we had no boulders, and we ran the flow in 60 liter per second and 80 liter per second. We measured 10 points, the red cross in the center and sides. In scenario 2, we used boulders with 1 meter spacing, again in 60 and 80 liter per second. Actually, this 1 meter spacing was equivalent to 8 times of a boulder, 8 times of a boulder diameter, or 8D. In scenario 3, we decreased the boulder spacing to 0.75 equals to 6D, and scenario 4, the spacing was 0.5 meter, equivalent to 4D. So to study mean and turbulent flow parameters, we use these parameters: mean velocity, time average velocity actually, the turbulent fluctuations that is useful to calculate some other turbulent parameters like roughness per velocity, turbulence intensity, and turbulent kinetic energy. Also Reynolds stressors that show how turbulent the flow is within the boulders. Also to study the eddy sizes, we use 2 parameters: Kolmogorov length scale. It shows actually the size of the smallest eddies. And also we use integral length scale that shows size of energy containing eddies, or large scale eddies. After that, we average the parameters in center line and sides for each scenario and flow rates. And also we normalize them to compare them in a better way. Results and discussion. After adding boulders, flow depth slightly increased, not too much. Maximum increase was 5%. Actually, this graph show in the x-axis shows the scenarios: 0.5 meter spacing, 0.75, 1 meter, and infinite means the no boulder. And y-axis show the parameter, the normalized parameter. After adding boulders, the streamwise velocity decreased. So, and also when we decrease the boulder spacing, the streamwise velocity decreased more. But no significant difference between scenario 3 and 4, means 0.5 meter and 0.75 meter spacing was observed in terms of the streamwise velocity. Also, turbulent parameters, roughness per velocity, turbulence intensity, and turbulent kinetic energy show similar trend. When boulder spacing decreased, these parameters increased. It shows actually higher velocity fluctuation and turbulence when we decrease the boulder spacing. Also, no specific trend was observed at the sides. Turbulence intensity has been an important parameter in some studies. They have used that to study suitability of a habitat for fish in terms of turbulence. So we tried to find a relationship between turbulence intensity and local average velocity. So we did it for each scenario, and we found very good relationships with high R-squared values, especially for the scenarios with boulders. We could establish a relationship between turbulence intensity and local average velocity, as you can see in these figures. And it was just for center line points, actually between boulders, because we didn't see a very good trend for sides. Okay, Reynolds shear stress. We call Reynolds shear stress in XZ plane principal Reynolds shear stress. And because it's usually have higher order of magnitude in comparison with other planes. So after adding boulder, it decreased, but after decreasing the boulder spacing, it increased. But the interesting thing was that order of magnitude of Reynolds shear stress in X, Y, and YZ planes was in some points similar to principal Reynolds shear stress. And it shows a 3D complex flow between boulders. At side points, we didn't see a significant change in X, Y, and YZ Reynolds shear stress. in eddy sizes. For eddy sizes, as I said before, Kolmogorov length scale shows the smallest eddies scales. This scale was larger at lower flow rates, but smaller at higher flow rates. And the order of that was 0.01 millimeter. It's very small. Also, this scale, Kolmogorov length scale, decreased after adding boulders, and it was very slight, this decrease. Also, integral length scale that shows the largest eddy size decreased after adding boulders, but it didn't vary by decreasing boulder spacing. And order of eddy sizes, the largest eddy sizes was 10 millimeter. So summary and conclusions. We actually observed just isolated flow regimes, and at the densest boulder spacing, we had some signs of wake interference flow regime. Velocity fluctuations increase after adding boulder, and it intensified at denser boulder spacing. Also, we found relationship between turbulence intensity and local average velocity, and we found that a scale of large eddies decreased after adding boulders. And it's important to consider that we cannot just decide based on the turbulence parameters. We should see the turbulence parameters aligned with also mean parameters, like mean velocity. For example, in our studies, you saw that when we decrease the boulder spacing, some turbulence parameters increased. It's not a good sign for fish. But we cannot just decide based on this, because also the streamwise velocity decrease, and it's important too. And we should actually see how they affect the specific species. We should consider both mean and turbulence parameters. For future studies, we are planning to consider more boulder spacing with a finer spatial resolution, because we couldn't cover all flow regimes in current study. And we want to see possible effect of boulder spacing on some specific fish species, probably some local species. And effect of boulder spacing and boulder arrangement on local sediment transport, bed load and suspended, that can affect water quality. And hopefully from next summer we will have a particle image velocimetry PIV system. With that we can study sediment transport and flow field around the roughness element with a very high accuracy. Okay, thank you.